We would like to compute the improper integral from 0 to infinity of e to the minus x squared over 2 dx. So this function does not have an integrand in a closed form. We would have to use a power series and integrate term by term. So what we're going to do to compute this integral is actually use a double integral in polar coordinates. So let's call this integral capital I. That means that I squared is this integral times itself. So the integral from 0 to infinity of our integrand. And now for the second copy, so I want to times it, I want to do multiply it by itself. So for the second copy, I'm just going to change the variable here to a different letter. I'm going to use y because the variable is a dummy variable. It doesn't matter what variable is used here. The value of the integral remains the same. So if I change that variable to a y, it doesn't change the value of the integral. And now we could think of this as an iterated integral, 0 to infinity of this is a function of x, that's a function of y. So we can change it into this separable integrand. So this function is separable, function of x times a function of y. So this iterated integral can be written as the product of the individual integrals. So I'm using the separable property in reverse, taking two ordinary integrals and multiplying them together. Essentially, this one is a constant. It can just come right inside of that one. And then this is a constant with respect to y, and so this function could come inside, it could come back inside of this one, and you end up with this. Okay, now this is the key moment where we recognize that this is going to be nice in polar coordinates, because if we combine these by adding the exponents, we get e to the power negative x squared plus y squared over 2. And x squared plus y squared in polar coordinates is r squared. So let's convert to polar coordinates. So we have e to the minus r squared over 2, and then dy dx or dx dy turns into r dr d theta. Now we're integrating over the whole plane here. X is between 0 and infinity, y is between 0 and infinity, so we're integrating over the whole xy plane, which means that r is going to go from 0 to infinity. R is going to go from 0 to infinity, and theta is going to go all the way around from 0 to 2 pi. So there's no theta in our integrand, so this is separable with r and theta, so we can integrate 0 to 2 pi d theta to get 2 pi, and then we have the integral from 0 to infinity of r times e to the negative r squared over 2 dr. So this integral is very similar to the original integral, except it's almost identical. The only difference is that here we have the presence of the variable, and here we did not have an x. And that makes all the difference because now we can integrate this using a u substitution. U equals negative r squared over 2, and du is negative r dr. So we get 2 pi integral. We need a negative r, so I'll put a negative here and a negative in the front. So we have negative 2 pi integral of e to the u du. And when r is 0, u is 0. And when r is infinity, u is negative infinity. So that's kind of backwards. And we have a minus, that's perfect. So we have 2 pi we will use the negative to switch the order of the integration, switch the bounds of the integration. So we have negative infinity to 0, e to the u du. There's our improper integral. And we have to write this as a limit. So we have 2 pi times limit as, let's say, t goes to minus infinity, integral from t to 0 of e to the u du. And this is 2 pi times limit t goes to minus infinity. Antiderivative of e to the u is itself. Plug in 0, that's 1. Plug in t, and that's t. And then as t goes to negative infinity, e to the t goes to 0. The graph of y equals e to the t is like this. And as t goes to minus infinity, the graph goes down to 0. So we get 1 minus 0 in the limit, which is 1. And so the answer is 2 pi. And so that was I squared. We computed the square of what we wanted. So that means, to finish it out, the original integral would be the square root of this number. So it's the square root of 2 pi.